Video, we're going over what many Chem 210 students consider to be the most challenging project of the course. But I want to tell you guys that this doesn't have to be the most challenging project. All this project requires is a lot of small details. You just have to be aware of them as you type your code. So I just really want to urge you guys to be very careful and to think through when you're typing this project, especially. That way we can minimize these number of small errors so we can diagnose them easier, and then ultimately you can complete the project easier. And because this is the most challenging project of the course, I'm actually going to split it into two parts. And I'm not going to go over any of the background math in order to help you guys understand how a bridge deformation actually works. I'm going to trust you guys to read the PDF, try and understand as much as you can before actually coming into this video. So with that, let's get started. So as you can see here, we have a one-section bridge, which in the project they say NOS, right, for number of sections. This is a one NOS bridge. And it consists of 10 fibers and 4 nodes, which I'm going to label A, B, C, and D. And so the real tricky part of this project is we have to create this matrix A, which holds the geometric information about the bridge. But what does geometric information really mean, right? That's kind of just mumbo jumbo. I'm going to show you guys what you actually need to do in order to create this geometric information. And the first thing we need to understand is the dimensions of matrix A. So the number of rows for A is equal to the number of fibers. And then the number of columns in A is equal to 2 times the number of nodes. So you should be thinking there, why is it 2 times the number of nodes? Why is it not 1 times the number of nodes? Well, for each node, we want to incorporate an X and Y value to that node. So what we're really doing here is we're actually associating 2 columns for a given node. And thus we have 2 times the number of node columns. So as you can see here, columns 1 and 2 correspond to A, right? So we have an A sub X value and an A sub Y value, right? We're encoding for both an X component and a Y component of that single node. Then columns 3 and 4, right? Again, 2 columns, one for the X component of B and one for the Y component of B, and etc. So of course, in this example, we're going to have 8 total columns, right? Because we have 4 nodes. So there, now we understand what the dimensions are for A, right? Number of fibers and then 2 times the number of nodes. But then how do we actually input these values, right? What are going to be the values for fiber 1? What are going to be the values for fiber 2, and etc., right? Well, we can go by this fiber by fiber. And so I'm going to show you guys an example for 1, 2, 3, and 4, and then you guys will be able to develop a pattern which you guys can then encode. So looking at fiber 1, okay. Fiber 1, right? The first thing we do is we look at our fiber and we check its angle with respect to the positive x-axis, which we're just going to say by definition stretches out this way. So as you can see here, fiber 1 has an angle of 0 degrees, right? So then, after we know that angle theta, what we do is we look at the nodes it's attached to. As you can see here, for this first fiber, it's only attached to node A. Remember, these 2 ends of the bridges don't actually count as nodes because they can't actually move when we deform the bridge. So again, fiber 1 is only attached to node A. And so now we have all the things we need to do in order to actually give the values for this first row. So the first thing we do is we take our node A, and that tells us what columns we're going to be working in, right? So then, since it's node A, we're going to be working in columns 1 and 2. And then what we do is we calculate the cosine and the sine values of our angle theta. So we do cosine of 0, which is 1, and that corresponds to our x value. So cosine of 0 is 1, corresponds to our x value. And then we do sine of 0, which is 0, and that corresponds to our y value. So look at that. So we did cosine of 0, 1, sine of 0, 0. And since that's the only node that's attached to fiber 1, we're done. We leave the rest of the values within the column as zeros, within the columns as zeros. So good. We finished fiber 1. Now for our second fiber. Again, what do? We first look at angle theta. All right, what's that angle there? And by definition, we're just going to assume that anything that's at a slant is going to be at a 45-degree type angle, right? So that's 45 degrees with respect to the positive x-axis, right? And then we look at what nodes fiber 2 is actually attached to, right? And it's attached to node B. So now we know the columns we're going to be working in. We're going to be working in columns 3 and 4 because those correspond to node B. And then what do? We calculate the cosine and the sine values of our angle theta. So what is cosine of 45 and sine of 45? Right? It's both 1 over root 2. And I'm going to call 1 over root 2s because we're going to be using this value a lot within the project. And so what do? Cosine of 45 is s. So then we put s there, right? And then sine of 45 is s. And that corresponds to our y value, so we put s there. And so now that we finished with the one node attached to fiber 2, we're done. We can leave the rest of these values as zeros. Now we're moving on to fiber 3. So here's fiber 3. What's this angle with respect to the positive x-axis? All right, well that's 90 degrees. Pretty good to work with, right? And then what nodes is it attached to? Well, as you can see here, it's actually attached to 2 nodes. It's attached now to both A and B. So instead of doing 2 values within this row, we're actually going to have to calculate 4 values. Right? We're going to have to put a value here, 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 and here in order to account for both the A node and B node being attached to fiber 3. So the first thing we do is let's look at node A, right? So let's calculate the cosine and sine of 90. So cosine of 90, right? 0. And then sine of 90 is 1. So we put in 0 and wait a sec, I put in a -1 here. So there's one thing you need to be careful about, and here's one of the big errors, right, that you might run into when you're actually encoding this. Getting the signs correct on these values is a little bit tricky. So I'm just going to give you a little shorthand method of actually just making sure that you have the sign correct. So for any of the y values that you might be working with, you can do this. So you look at your fiber, and if the node you're working with is below the fiber, you're going to put a negative value for that y value. So since A here was below fiber 3, that's why I put the sign value as -1 and not as regular 1 as we had originally thought it was, right? So since A is below, we put a -1. And the same goes for node B, right? If it's above the fiber, the y value is positive, right? So since this is above, we're going to have a positive sign value. And then, so for that y component, it works the same for the x component, right? So if we have a node to the left of a given fiber, we're going to make that x value negative. So for example here, if we were working with fiber 7, and we saw that node A was to the left of it, we can make the x value of that node A to be negative, because it's to the left. And then again, if it's to the right, then we can make it positive, because it's to the right of that fiber. So again, continuing on with our example of fiber 3, right? So we calculated both the cosine and sine of 90. So we got cosine of 0 is 0, and then we got sine of 90 is 1, but then we changed it to a -1 because it's below this fiber 3. Now let's look at the node B, right? That's also attached to fiber 3. So again, we do cosine of 0, which is 0, good. And then we do sine of 0, which is 1. And then we check. Node B is located above node 3, or fiber 3, so we make it a positive value. Good. Now we're done, right? We worked with both nodes A and B, and we got all their values, so then these can be left as 0. And now our final example out of the bridge is we're going to do fiber 4. All right, looking at fiber 4. What's this angle with respect to the positive x-axis? Okay, we don't even have to do that, right? You know, it's a little bit bigger than 90, but we know that these are all at 45 degrees, right? So we're just going to be working with s, right? The only important thing is we need to figure out if the s value is positive or negative, right? So we're working with nodes C and B, and so let's work with node B, right? So as we can see here, node B is to the left and above fiber 4, right? So since it's to the left, it's going to have a negative x value, and since it's above, it's going to have a positive y value, sorry. So as you can see here, for node B, a negative x value, again, because it's to the left, and a positive y value, because it's above fiber 4. And so good, that's node B out of the way. Now let's look at node C. Node C is to the right and below fiber 4. So since it's to the right, it's going to be a positive x, and since it's below, it's going to be a negative y. Positive x, negative y. Okay, good. We finished both of the nodes on fiber 4, so we can leave the rest of these as 0. And so those are just the first few fibers, right, in the bridge. I'm going to trust you guys to figure it out for the rest of these fibers within this bridge, and then, again, for the fibers if you have an even longer bridge. And here's a good hint, right? Is once we add in more sections, a pattern begins to form, right? We're going to have these same crisscrossing fibers, same horizontal fibers over and over and over. So what you can do is you can use a loop. So you only have to encode it once, but then you can say, oh, I want to have a bridge that's like 10 sections long. And it'll just be able to do that pattern over and over and over. So that's what you need to think about, right? you're going to be seeing this pattern repeat over and over and over for a few times. So what you can do is you just need to create this matrix, right? And then say, make it bigger for the more number of sections you have. So I'm going to leave that to you guys to try and figure out. So anyway, that's matrix A, right? Encoding the geometric information. That's the trickiest part of this project. But we also have a couple other matrices we have to work with. And so let's go over those too. So we have this matrix here, x of c and y of c. What do these do? Well, these hold the coordinates of each of the fibers within the bridge. So as you can see here, we have fiber 1, and then there's 4 values along with it. And so as you can see here, there's a column x1, x2, y1, y2. So what do x1 and y1 correspond to? Well, that corresponds to what I'm going to call the lower valued side of our fiber. So as you can see here, fiber 1, right? Here is going to be x1 and y1 because I'm considering this the lower valued side because it's like further to the left and it's not associated with a node. And so this here is actually the origin of our graph. We're just going to consider that by definition. So x1, y1 is 0, 0, the origin. And then x2, y2 is going to be the higher valued side of our fiber, right? So as you can see here, the other side of the fiber here is located in node A. And so node A is the higher valued side, right? It's further to the right and it has more preference because it has a node associated with it. And so what's the coordinate of that? Well, if you remember within the project documentation, we're considering the length of these fibers to either be 1 or in the case of a slanted one to be the square root of 2. So we can actually figure out the coordinates of this end of the fiber. And it actually turns out that the coordinates are 1, 0. So as you can see here, back on this side, the coordinates are 1, 0. And so I'm just going to give you another couple examples just to make sure you guys get it. Fiber 2, right? All right, looking at the lower valued side, right, for x1, y1. Fiber 2. Well, the lower valued side is, again, the origin, so it's going to be 0, 0. And now the higher valued side is up here at node B, the more preferential side, right? And so what are the coordinates of that? Well, this is 1 length and this is 1 length. So we can figure out the coordinates, so that's 1, 1. And we get 1, 1. And then finally for fiber 3, what's the lower valued side? Well, as you can see here, this is a little bit more tricky, right? But the lower valued side, again, by definition, is going to be at node A, right? So then x1, y1 is going to be 1, 0. And then what's x2, y2, the higher valued side? Well, that's going to be at node B, right? So that's going to be 1, 1. And so then again, I hope you guys can see that there's kind of a pattern forming. So you're going to have to do this for each fiber, right? And then soon you're going to see that this pattern will repeat for a larger number of sections of bridges, right? It's just going to get higher and higher in numbers, but the same general pattern is going to follow. So again, you guys can figure out how to encode for XC and YC for any number of section bridge. And then the final matrix you're going to have to work with is this Len Matrix, which encodes the length of the fibers within the bridge. And this one's probably the easiest out of all of these matrices to work with. And so, again, this is fiber 1, this is fiber 2, this is fiber 3, etc. So remember, by definition within the project, anything that's a horizontal or vertical beam is going to be of length 1, and anything that's a slanted beam is going to have length square root 2. So as you can see here, the length of fiber 1, since it's horizontal, is 1. The length of fiber 2, since it's diagonal, is going to be the square root of 2. And then the length of fiber 3 is vertical, so it's a length of 1, and etc. So again, a pattern is developing here. You guys need to figure out how to encode this pattern for any size bridge. And so that's about it for this first project, right? So what did we go over? We came up with this matrix A, right? We figured out its dimensions, and we figured out how to input the values for a given fiber based on getting this value or the angle with respect to the positive x-axis and figuring out what nodes our fiber is attached to. Then we looked at our XC and YC matrices, which actually give the coordinates of each fiber, right? As we can see here that there's a left side of the fiber and a right side of the fiber, or maybe it might be better to say the lesser valued side and the more preferentially treated side. And so those just hold the coordinates, right? And then we finally have our length matrix, which encodes for the length of each fiber within our bridge. And so remember here, this example that we went over here is only a 1 NOS bridge, right? 1 number of section. But in the project, you're going to have to go up to 3 sections big. So what you can do is you need to figure out how to actually figure out what this pattern is and then repeat it using like a for or a while loop. So that way you don't have to write huge number of code, right? Huge number of lines of code. You can just write a few lines of code and then tell it to loop. So then it'll keep building a bigger and bigger matrix which follows this pattern. So that way you can represent a larger and larger bridge. And with that, I hope this video helped. And I'll talk to you guys in the next one.